my friends, let's have a look at interesting exam question from recent year. Okay, and this question can possibly extend for a very interesting idea with internal assessment. So let's take a look. Okay, so I prepare the exam question as well as its proof in the animation, and then possible question for the internal assessment. So let's get to it. All right, so this question came from November 2022, and in this question, first you have to prove the sum of arctangent becoming the single arctangent using the trig identity such as a compound angle. Okay, and then here I think I forgot to mention here the complex number. Okay, was given as n squared plus n plus 1 plus I. So that's the real and imaginary part in the Cartesian form. And then if the omega was, the product of those complex number, what you had to show was the argument of that would come up to be the following sum of the arctangent. What is that? Well, first of all, the proof of that is pretty straightforward. I mean, this is just the sum of arctangent, and every time you have an inverse trig, so please consider this as an angle, right? So you are looking at angle here, right? And then every time you have a sum of the angles and wanna somehow induce some identity, it's probably better to composite with a trig identity, such in this case will be tangent, right? So I composite with the tangent, and then you can open this as a compound angle as the following, and it's good to go. All right, so that's great. And then here, if I do the compound angle of tangent, and please remember the property between the function composition between the function and inverse function, so it would just come out as A, B, etc. So that's what we have. Right? If you compare with the right-hand side, it's also the same as if you composite with the right-hand side by the tangent, cancels out, we have the form that we wanted. So that's how you can, combine the arctangent into a single identity. No problem. That is. So let's move on to the next. So here then the question goes, okay, then we have complex number as we defined before, and then the omega represents product of all those complex number, right? And I want to show this by induction, right? That the argument of that is going to be given as the single arctangent n plus 1. Okay? So for the induction, as you know, we got to go with the induction the basic step first. So n equal to 0. So that's when argument of the omega 0. That's just the 0 note, right? Because the omega n was the product of the following form, which I can put it as maybe as a capital letter pi for the product. Right? So it's the same as that. Okay. And for the first term will be the z naught, where Zn was defined as 1 plus n squared plus I. So if you let the n to be 0, then I have 1 plus I. So that's my complex number, and for that the argument is pretty obvious that it's gonna be pi over 4. And if you use the given statement here, it was, I believe, arctangent n plus 1, and if you let n to be 0, as you can see, you get the arctangent 1, which is also going to be simply just pi over 4, right? So easy to prove it for the basic step. Now I'm gonna for the induction hypothesis. Now I'm going to say the argument of z naught up to zk is gonna give me the arctangent k plus 1. Then what's gonna be the result to prove is what we wanna discuss. Okay, so let's take a look. So arctangent omega k plus 1, right? What is it? It's omega k. So omega k plus 1 by the definition is the product of a complex number, isn't it? So I'm gonna go with z naught z1 going all the way up to zk, and then zk plus 1, right? So that's great. So then, however, I can now describe this as omega k, right? So I got the omega k here, and then I multiply the next term of zk plus 1. That's great. But again, the argument here of a complex number, if they're product, we can actually convert into the sum. Likewise, if you divide the complex number, the argument will be given as difference. No problem. So that's great. Now I got the argument of omega k, which I can use the induction hypothesis. I believe it was arctangent k plus 1. And then here I'm using the definition of the argument of complex number, which is arctangent of the imaginary part of the real part. Here the real part will be replacing the n with k plus 1. So instead of writing down this as a n squared n and 1, I'm writing down k plus 1 squared plus k plus 1 plus 1. That's great. And so now I got to simplify, and we are going to use the identity we learned from the compound angle, which I can put it into the single arctangent. So I got this messy, very nasty expression here, but obviously now the essence is in the simplification. But here's the thing. One comment about the induction is that you already know the answer, right? So you already know the arctangent k plus 1 should be raised to arctangent k plus 2, right? So what I'm suggesting here is that what you have in this nasty expression must be simplified enough so that you're going to be just left out with k plus 2. So therefore, even though the simplification seems challenging, when you already know the answer for the induction, it's not too bad, right? For the induction, the essence is where you show the steps, not the answer, because the answer is already given, that it has to be simplified to the k plus 2. Right, so that's correct. So let's take a look how it does it. So if I go to the following form, maybe I will multiply by this polynomial term top and bottom because I don't want to deal with the fraction form in top and bottom, so which I just did, right? By multiplying the k squared plus 3k plus 3 on the top and bottom, I'm left out like that, right? But here I don't see common factor well, so what I would do is to expand and simplify further. So let's do that. So if I do that, what I'm given here is this is my arctangent. So now what I must know is that this must be factorized by k plus 2. Otherwise, this is not going to cancel out and leaving the k plus 2 out. So you know what? Let's before I show you this, let's try to factorize the numerator by knowing that I gotta have a factor with the k plus 2. So if I have 1, 4, 6, 4, and knowing the k plus 2 being a root, it must have a negative factor. It must have a root of negative 2, and I can do the synthetic division. So 1, and I'm going to multiply. It's going to be negative 2, 2, negative 4, 2, negative 4, 0. Okay, so that's great. So then I have, then this is going to be k plus 2, and then the second factor is going to be k squared plus 2k plus 2, right? That's great. So here, I got the form like that, then I can cancel this one out, no problem. So now I got the k plus 2, just like this, right? So then here I can replace the k plus 2 as a k plus 1 plus 1, and boom, this is exactly what I have, okay? So then, for the induction, please remember you need to go through 3 stages. The first step is to show the basic step works. It doesn't necessarily have to be n equal to 0 or 1. It depends on the case. And then the induction hypothesis assumed to be true should imply the result to be true. And then the third one is the conclusion that because we since we show the basic step and implying n equal to k implies n equal to k plus true, k plus 1 true, the statement is true by the principle of mathematical induction is what we have. Okay, so that's correct. Okay, so that's nice. So now what we want to do is to have a look at the proof of last statement in geometry, and especially when n goes to infinity, what's going to happen? Well, we can sort of guess, right? We just show by the complex number and working with the extensive algebra that the sum of arctangent, sum of the argument will converge to the can be simplified as the sum of arctangent n plus 1. And if you send n to infinity, that becomes what? Arctangent infinity. It becomes giving you the pi over 2, right? So that's the sort of a proof I want to show you in geometry. So let's quickly show you using the right angle triangle. So here what I've just prepared for you is a right angle triangle with the base length as a 1, opposite as an n, and the hypotenuse as h, okay? So what I've then tried to do is to create n squared plus n plus 1 many of them. Now, how many of this? I got the n squared plus n plus 1 many right triangle. All right. So what does that do? Then you can actually see the the base of this large one, right? Because it had the unit length was 1, and I have how many? The n squared plus n plus 1 many. So 1 times n squared plus n plus 1 would be the base, and then here the opposite was n. So n times that many will give you the opposite. No problem. And what's the benefit of knowing that? The benefit of knowing that is going to give you the coordinate there. So this coordinate now is going to be, n squared plus n plus 1, the x coordinate. And then the y coordinate will be the multiple of n on top of that. Right? So that's what I've got. And then the next thing I actually want to talk about before we proceed is the angle here. Please remember this angle is going to be it's a similar triangle. So I can use just, smaller triangle, which is got the n and over 1. So if I call it theta, then theta should be arctangent n. So now I got the argument here, angle as arctangent n. Okay, what I like to do that is I'm going to rotate this pi over 2. So this is the triangle that I have exactly congruence, but just rotated a bit. Right? I got the opposite here as a hypotenuse. Hypotenuse h. That's great. Then here, this was also the hypotenuse. But how many of that do we have? We got, h times, and then the n squared plus n plus 1. Right? So I got that many of the hypotenuse. That's great. Then I'm going to create a right angle triangle like this, and I got the argument phi here. And what I can do with the argument phi there is that, boom, I got the h times how many? N squared plus n plus 1, many of it, right? Then that's going to be the adjacent of this red triangle. And what's the benefit of knowing the adjacent? Well, I got the opposite. So if you see their ratio, then you can see the tangent phi, right? So then h cancels out. In fact, the angle that you see there, phi, is the same as arctangent of 1 over n squared plus n plus 1. Okay, so that's great. So that's the argument there. That's the argument of arctangent 1 over n squared plus n plus. And what I'm interested in is, okay, what happens if I add this argument? So now I have here the arctangent n, right? And I got here the arctangent of 1 over n squared plus n plus 1. That's great. And I want to know what's going to happen if I add them. Well, for that, I need to know another triangle here, okay? So on this right angle triangle, then if I knew this coordinate there, then I can do the rise over run. Well, now I'm shifting to the left by n, isn't it? So I already had the x coordinate here. What I like to do is just subtracting by n. So the x coordinate there will be n squared plus 1, okay? So that's great. So what about the y coordinate? Well, I had a y coordinate there, but I went up by 1 unit. So I would just simply add by n cubic plus n squared plus n, what is it? Plus 1, right? That is lovely. So then I know the adjacent and opposite of the second, the largest triangle we see in the triangle. And then if I call this angle here as, let's say, I don't know, omega, but maybe not. Let's call it as an angle gamma. Then tangent gamma, right, is going to be the rise of a run. For the rise, it's going to be the y coordinate. Well, for which I can just write that, but maybe it's, if we could factorize, I'll probably factorize that, which it seems like it has, because for the first two terms I can factorize by the n squared. That's going to be n plus 1, and then the next two terms will be the n plus 1, right? So then if I factorize that, I'm going to have n plus 1, and then I got the n squared plus 1, right? So that's great. Over, and if you look at the denominator, that's going to be n squared plus 1, and that's lovely because I can actually cancel this out, right? So then I have a gamma being who? Arctangent of what is it? N plus 1. So that's great. So now you see that the sum of the arctangent n and arctangent 1 over n squared plus n plus 1 will be actually the arctangent of n plus 1. We can actually prove it just using the geometry without using the compound angle. And then what it do? Well, if you rearrange the arctangent n maybe to the right hand side, you got the single arctangent form, and you can actually figure out what is it? The sum of the arctangent, what is it? N squared, 1 over n squared plus n plus 1, right? So that's the identity we have, and then let's try to see what's gonna happen if you keep adding those angles, right? If you continue to add those angles, what you actually realize is that let me quickly show you first few steps. That's the first term, the second term, third term, and it goes on and on and on. If you do infinity many times, in fact, you realize that this actually will become, what is it? Pi over 2. This actually becomes pi over 2. So that is another proof of what we had seen from the complex number with the argument versus the geometry, just using the right angle triangle, showing you that the arctangent of such a triangle would actually converge to pi over 2 if you add all the angles. Okay, so that is amazing. So we started off with the exam question, but we give you a geometric proof with the arctangent. But number 3 is, why do we see so many questions like that? In fact, not only the November 2022, but also in May 21, you see the same question over and over again. In this recent exam question, you also again had to prove the compound angle identity with the arctangent, and somewhat add with, what is it, the arctangent of this rational form becoming a rational form of the arctangent. Okay, why do we see that often? I mean, there's a strong connection with complex number. Well, to be more precise, complex analysis. So if you're interested in, you can actually link those ideas with summation of a certain number, okay, becoming a single expression, such as, what we previously seen here is that it becomes sum of arctangent 2 of r squared is becoming the arctangent of n over n plus 1. You can actually show that with other examples, and I'm about to show you that. Okay, so let's have a look why we see so many arctangent series becoming a single term. Okay, so what we can do is remember in the first question what we saw was the omega n expressing as a product of a complex number, right? So that's what we saw. And then for the complex number, if I write things in the Cartesian form, it's given as such. Okay, but if you want to find the argument of it, right, then you know that the product of a complex number their argument will be the sum of it, right? And also the sum of a complex number, if I call that as a z, and the argument of z will be in fact the arctangent, the inverse tangent of bk over ak. So that's what we have, isn't it? Right, so that's what we're going to do. You know, we can actually introduce the inverse tangent for the process of the argument like that. And then if you ask me, okay, when are you ever really interested in the product of a complex number? It's often to do with the roots of unity, right? So let me quickly show you. If I have a z to the power of n minus 1 polynomial special case, then roots of unity is given as that. We already know that, right? And then if you actually do the argument of roots of unity, you can change into the sum of the following inverse tangent form. And that can be actually utilized, modified, and sort of you know, if you put some interesting algebraic skills, algebraic manipulations, and then you can actually induce a very interesting series, like what we saw from the exam questions. Okay, so let me quickly show you the connection of this roots of unity, the argument summation, and with the arctangent. Okay, so I'm not going to delve into too much details of this, but let me show you an example here. So if you know, imagine that I got this following polynomial sine pi z. Okay, then you know, you can already figure out the roots of it, isn't it? So because, you know, in order for sine to be 0, then you know the inside where pi z has to be, what is it, integer pi. It has to be integer pi, isn't it? So that's great. So then pi cancels out. K is going to be just plus minus 1, plus minus 2, exactly. So that's lovely, okay? So in fact, you know, so then, you know, if I have a root, you know, what do? You know, what we typically do here is a z minus 1, z minus 2, z minus, sorry, let me actually make it better. You know, this can be factorized as a z plus 1, z minus 1, z plus 2, z minus 2. So it goes on and on, and plus minus the integer multiple. So here, then this can be put it into the difference of a square, and that's how my factorization looks like. But it's not exactly the same, because this factorization is actually wrong, simply because it's too large. Right? If you actually look at the constant term, it's going to be product of the integer square, where you see that the sine function cannot get too big like that, especially when he comes with the y-intercept. So we actually had to reduce it down, you see. But you know, too much. I'm not going to get into too much detail of that. But that's how the factorization is going to look like if you have integer solutions for the sine, and then we had to put it into like 1 over k squared like that, so that you can actually end up having the, what is it, the y-intercept being 1. When you divide by the pi z. No problem, no problem. But now, if I see this, the product of it, and if you actually want to find the argument of that, then the solution is going to be, the expression can be put it into the sum of the arctangent as the following. And if you see this expression, it looks very fancy. It is fancy, but it's not that fancy. It's definitely doable within the math that you learn in school, because you already extensively learned with the complex number trigonometry. Okay, but yes, we do have one or two more interesting expression like the hyperbolic tangent. Don't worry about it. I'm not going to talk about that now. But if you're interested in for your IA, it's definitely a worthwhile. It's worth studying for. Okay. So then, you know, with that expression, you know, let me quickly go into the other form. Yeah, if I go into the half, what it can give you is the following expression. In fact, that's the exam question that you saw in 2021, right? In the 2021, you actually had to prove it, that this actually becomes pi before when you send the n to infinity. But in this step here, what we showed was actually generalizing it using the tangent, arctangent, and hyperbolic tangent. It's very interesting. So the use of those expressions, the unseen function, can simplify the expression into the form. So even if I didn't know that it was a arctangent n over n minus 1, you can still show using this identity we proved from the complex number to show the convergence becoming the pi over 4, right? Because in the exam, remember, you were already given that the arctangent sum becomes that, right? But what if I didn't know that? Can I still derive it? Then that will become a bit more challenging problem, which you can associate with the complex analysis, and furthermore possibly the Ramanujan series, where, you know, remember the 1 plus 2 plus 3 plus in the complex number, you can actually prove it that it becomes somewhat the negative 1 over 12, and you know, it's a very interesting discussion in using the complex number. Okay, but yeah, you know, I just wanted to show you 3 things. Okay, that exam question, very nice one. right? But it's been very popular. And then the second one is proof of that using the geometry. And the third one is possible extension. Why do we see that often? Well, because the examiners wanted to show you that you'll be learning this kind of stuff in the complex analysis when you go to college, right? But obviously, when you have a series, to show what it becomes is actually very difficult, right? But when you have the answer, showing that by induction is doable, right? For example, you might have seen this once or twice. That k is equal to 1 to n, k squared. You often prove this by induction with the n plus 1, 2n plus 1 over 6, right? But the question is why? I mean, we can definitely prove this by induction, but how can you come up with this in the first place, right? That's more challenging, and that is definitely something you can do with the internal assessment. And for this one, you might want to take a reading on something called Flower-Haber. Let me quickly write Flower-Haber's formula. It's something to do with the combinatorics as well as a very nice challenging topic, something called the Bernoulli number, and then that summarize what I want to talk about today. So yes, a very interesting example indeed, and I wish that this proof as well as extension can give you some idea for your not only the IB study but also for the internal or extended lesson. That's pretty much it from me today. I will see you. Thank you.